All right, if I go to the next one though, notice how this is still the harmonic series, but it's going to be alternating. So while this is the harmonic series, this is also a well-known series, and we would just say that this is the alternating harmonic series. So let's write out these first few terms. So if I let n be a 1, the first thing I'm going to get is a positive for the exponent part, the alternating part, and then I would get 1 over 1. So that's the first term. If the n is then a 2, it's going to be a negative 1 in the numerator over 2. And then we alternate to 1/3, alternate to a negative 1/4, so on and so forth. Look at your sums now, sort of understand where these would have come from. And when we do this, I want you to graph this. I think the graph makes this a little easier to see how this is working. So if I ask you to graph just the first sum, that sum is the first term only, and the first sum is a value of 1. If I ask you to graph the second sum, then that's just us adding the first two terms together. So 1 and a negative 1/2 is why we get a half. So the second sum would be halfway up. Our third sum, which is 0.833, is us then adding the first three terms together. So if we did 1, negative 1/2, and 3, adding them all up, we see what we have here is 0.833. So now we're up here. The fourth one, now we go ahead and combine the negative 1/4 with that. That would give us a value of 0.583. So that should be a little bit bigger. Here was our half. So it should be a little bit bigger than that. And then let's do two more. The fifth sum would have been 0.783. The sixth sum would be 0.616. You can graph the next few if you want. But what I want you to do, and I think it's easier to recognize by graphing this, that doesn't this appear to be converging to something? It's going from above it and below it, but there certainly appears to be some sort of value in here that we would be approaching from both above it and below it. So while the harmonic series definitely does not converge, what we are finding for the alternating series is that the alternating series does in fact converge. All right. So what this section gets into is, and we haven't really dealt with these last couple of days with all of our tests, our alternating series for these. Maybe a geometric we've talked about, but that's about it. All the other ones would have been all positive terms. So if it is an alternating series, it is easier for our series to converge, and we just saw that here. We just took a series that diverges, the harmonic series, and by making it an alternating harmonic series, we went from diverging to converging. So the alternating part of this makes things a little bit easier to converge. So this first one here, when it says the alternating series theorem, notice how this is our alternating component of this. So you can also do cosine of pi n's, negative 1 to the n, as long as this means we're alternating, and then our general term. That series will converge if the following three conditions are met. So the first one is that the a sub n's, so understand what that means. That's the non-alternating part right here. Those have to remain positive all the time. If those are always positive, and then you have this little negative 1 to the n in front, that would ensure that we are going to alternate throughout the entire sequence of numbers. 2 and 3, largely for what our understanding, need to say pretty much, are saying the exact same thing. That whatever the second, so whatever the this term is here, has to be greater than or equal to the next term. So if n is a 1, so that's this guy here, and I let n be a 1 here, well, a sub 1 better be greater than a sub 2. It's really a different way of thinking that our a sub n's still must go to 0. So in layman's terms, all we need to make sure of is, do we always alternate? And that would be making sure that this guy by itself remains positive, so that the negative 1 to the nth power will ensure we alternate. And then 2, it just needs to pass the nth term test. So as long as we alternate and we pass the nth term test, we can say that we converge by way of the alternating series theorem. All right, so with that thought, go to number 2 first. Number 2 is one I'd like to kind of start with. As soon as we see that this is a series that should be alternating, if we want to be using the alternating series theorem, the only thing then that we are concerned about, it's two things. Is what's inside of here, the non-alternating part, would this always spit out positive numbers all by itself? So if we start at n equals 1 and then 2, 3, 4, 5, 6, then yes, this should always spit out positive numbers. That's what this first condition here is saying. The second condition is, as we check our nth term, so as n goes to infinity, will this overall then approach a 0? So notice this has a 1/2 degree in the numerator. Our degree in our denominator is smaller than that. So because of that, the faster growing function is on the bottom. This does have a limit of 0. So we are alternating the whole time. It passes the nth term test. So we can now simply say that this guy converges. And right now, all we would need to say is the alternating series theorem. All right. So for the moment, at least these next couple of questions, we don't have to worry about all those other tests yet. All right, so now go to number 1 and we'll do one that doesn't work. So now the n term is that 1. So that's our general term, the non-alternating term. So we've satisfied this first condition, but then the second condition is, as we go to infinity, this non-alternating part better have a limit of 0. It better be going to 0. Well, it's a constant. The limit of any constant is that constant. If I can get this to work. So that diverges. You can write the word diverges while I try to get a pen that's going to work. Oh, because I'm on the eraser. Never mind. Yeah, so this should have a limit of 1. So we're going to say right away that this diverges. And then since it doesn't pass the alternating series theorem, we just revert back to our old ideas that the nth term test, how we know this fails, and the reason we know that fails is as n goes to infinity, we want to state what limit this would be producing. So we go 1, -1, 1, -1, 1, -1, so on and so forth. That limit does not exist. We just bounce back and forth between 1, -1, 1, -1, 1, -1. So that doesn't exist. All right. All right, 3. Let's rewrite this first. We always want to do that with a common log. It's the same here. So whether we were doing derivatives, E&I derivatives, I always told you to rewrite this thing with the change of base formula. We still want to do that. Actually, do this for me too, now that I look at this. Take this n equals a 1 and have it be n equals a 2 so that we don't have an undefined term to start this thing off with. All right, so again, what we're simply looking for is look at the non-alternating part. So if I look at these two divided by each other, we want to make sure those are going to spit out nothing but positive numbers, and they will. So if I let n be a 2, 3, 4, 5, these will always spit out positive numbers. So first thing is good. Then this non-alternating part better have a limit of 0. And if it does, then it converges. If it doesn't, then we say that it would diverge. So it looks weird. First time we really probably have done one of these. And we've talked about the natural log. He's pretty slow. He tries real hard, but he loses most of the time. But do we agree the natural log does, in fact, go to infinity? Yeah, he just does it really, really slowly. Well, if you look at your numerator, isn't the natural log to a constant? So that's not changing at all. So that's about the only way that a logarithm could win, is if it's up against a constant that doesn't actually ever change in value. So the faster growing function is on the bottom, basically because the numerator doesn't grow at all. It's always a natural log of 2. So that does pass the nth term test. So we've satisfied those two conditions for the alternating series theorem. So we just say converges, and then we just write that in, alternating series theorem. All right. So number 4, real quick, see if we're understanding kind of what these conditions are and determine if number 4 would work. Actually do 4 and 5. They're both, these are all pretty quick. Also, real quick, because sometimes people ask about this, and I don't want to spend too much time with it. N equaling a1, wouldn't that give us a 0 term at first? And then the second term would be the natural log of 2 over 2, and then the natural log of 3 over 3. If we really wrote those out, we wouldn't be putting a 0 right here, because some people will say, no, they're not always going to be positive. But the reality is this would end up being our first term. So these are going to all be positive values. Don't think of that 0 as causing a problem with that first condition. Okay. All right. So for both of these, we see that it's alternating. So that's the little -1 to the n plus a 1. That kind of loosens our restrictions a little bit. All we then have to determine is, does the non-alternating part, so the ones that I have in blue, do those pass the nth term test and stay positive the whole time? So they're both going to stay positive the whole time. As long as they pass the nth term test, we are good. So in this one here, does this go to 0? Is our faster growing function in the denominator? Yeah. So this one, we should say it converges. You don't want to abbreviate this much, but save a little time since you've already done this. Alternating, I have that backwards. Alternating series theorem. All right. When we go to number 5, same thing. Here's our alternating part. This term here for sure is going to remain positive all the time. So the only last thing that we need to check is, will this thing go to 0 as n goes to infinity, or basically does it pass the nth term test, and does it? No, definitely not. That faster growing function is on top. So this is infinity. So when we justify the fact that this diverges, it's because of the nth term test. One of the bigger mistakes people make, did I already do one of these? Yeah, is when we come here, people thinking that this limit is infinity. But when we put these two ideas together, the fact that we're alternating, this is a limit that wouldn't exist. All right, so that's why that diverges, because of the nth term test. Now, last year, we would be done with these notes because the next page is something that the AP test took off of the test. However, you guys need to know this. So on the next page, you are going to see, and it's going to look really weird. Now, these first two little bullets are going to sound odd when we do it. So just kind of follow along, and I think once we start doing some problems, it's not that bad. If you have an alternating series and it converges, so here's our alternating, here's our general term, and that converges, and the absolute value of that series converges, so that's what this is saying. So if that absolute value converges, then we would say that that series converges absolutely, because the absolute values would work. All right. If the alternating series converges, so if our alternating series does converge, but the absolute value of that series would diverge, then the series converges conditionally. The easiest way to explain that is the one that we did on the front page. So if I look at this, remember this is the alternating harmonic series. Remember how we said this converged on the front page? We saw that visually with our little graph that definitely converges. What the conditionally versus absolutely is basically then saying, if I got rid of the alternating part, could the series on its own, if it wasn't alternating, would this be a convergent series? No, right? It's the harmonic series. So it only converges under the condition that it is alternating. If it wasn't alternating, then we would have said that this guy diverges. But this condition that we alternate is going to allow this one to converge. And when that's the case, you would write that it converges conditionally. Okay? So with that, let's try to keep these straight. Let's rewrite this one real quick, just for the sake. I think it'll be easier to understand. 0.1 is a 1/10 to the nth power. So let's write that like this. This is an alternating series. All right. So what we're now concerned about is, does this guy, let's actually write it one more time just to make sure we understand this. 1 to the nth power would be a 1, and then 10 to the nth power would be an n. So the first thing is what we did on the front page. Does this thing converge? And it does, because it's an alternating series. This will always spit out positive numbers if it was by itself, and then the faster growing function is definitely on the bottom. So we would definitely say that this converges. But what we now have to do is add whether it converges absolutely or if it converges conditionally. So what that then would entail is, and don't necessarily erase yours, but if I erased the alternating part, would either one of these versions or the same exact thing, would that converge on its own? Is that a convergent series all by itself? Yeah, okay, I got a couple heads nodding, because isn't this kind of a classic geometric series? All right, so this by itself would converge. So that means it converges absolutely. Even if they were all positive terms, it would converge absolutely. And then we would now need to state why, and that is because that series that we're looking at is a geometric series with a common ratio of whose absolute value, absolute value of r is equal to 1/10, which is less than 1. All right. We clear on that? Any questions with that first one? Okay, then 2. Here's our alternating part. So then all we have to focus on is, does this guy here spit out positive numbers exclusively, which it would? And then does this guy here have a limit of 0 as n goes to infinity, which it would, because we have a constant on top. The root n is going to grow to infinity. So this does converge. And if it was the front page, we would just say, yeah, because the alternating series theorem. But if I'm now asking you specifically if it converges absolutely or conditionally, now we need to fill this in. So what this then implies is that, let's pretend this isn't here. Would this guy converge on its own? Write down what you think. Let's see if we recall this. Because I'm in so many different places with videos for both classes and we're day off. I want to say this was in that previous day of notes. So we'll see if you remember what I talked about in that video. All right, then, do you remember this little guy, the p-series idea? All right, p-series is the whole 1 over n to the p. That's what I have right here. I have a 1 over n to the 1/2. The p is your exponent for that denominator. If the p was a 1/2, did that mean we converged or diverged? And you have the notes right there. You can flip the page. What did we do? Converge or diverge? Like, did we converge or did we diverge? I don't think I have those notes. So, oh no, it was the first day of notes. We should all know that, right? Here it is. P-series. All right, if it is less than 1, it diverges, right? So that's what we're dealing with right here. So that guy diverges on its own. Right? So that means it only reason it converged is because of the condition that it was in fact alternating. It's a ratio test that you guys should have looked at yesterday. So that converges conditionally. And then we would say, because this is a p-series with a p equal to 1/2, which is less than 1. And as the p-series go, that's a bad thing. 3 should be a nice one. This is alternating, so we've satisfied that idea. This will spit out nothing but positive numbers, so we've satisfied that part of it. So the last little element here to determine if it converges or diverges is that this series has to approach 0 as n goes to infinity. So will this non-alternating part go to 0 as n goes to infinity? No. So this one diverges right away. The faster growing function is on the top. That causes us to fail the nth term test. The limit as n goes to infinity. Again, don't say infinity here. Usually on the partner quiz and this quiz, that's one of the more common mistakes. The non-alternating part would be infinity, but because overall it is alternating, that's going to make our limit not exist. All right, so that limit does not exist. All right, number 4. See what you think for number 4. Forgetting one. All right, so here are the tests we currently know. First, though, does this converge? In terms of just does it converge, will this satisfy all those conditions on the front page? Yeah, we alternate. This is always positive. This will have a limit of 0 as we go to infinity. So this definitely converges. So that's the easy part of this. And then it's now determining if this wasn't here. So if I got rid of the alternating part, would this guy be okay on its own? And to determine if this guy is okay on its own, now we got to revisit all of these other options. Definitely not geometric, so it's kind of through a process of elimination, we can get rid of this. It is not a p-series, because that has to be a constant in the numerator and then just your variable in a denominator, so we don't have that. You could try to integrate that. That'll keep it busy for a while. You could try use substitution. Integration by parts, partial fractions requires this to factor nicely. You're not going to get linear factors from this, so you can't integrate it. So then we're left with yesterday's thing and this one. And as I said in the video, these are the two that people, as we look at the comparison, we always want to avoid it, and they like doing the ratio test. But it is the comparison test here that's going to work out the best. And what we're going to do, remember how we did the comparison test. And the reason this kind of screams out comparison test a little bit, see how we have this little +1? That's typically how we want to approach a comparison test, is by just dropping out a number someplace. We've kept the numerator the same. We've kept the denominator the same. Or we tweak the denominator with that little +1. What we've identified, if the numerators are the same, this denominator is always a little bit bigger than this denominator, then overall, the one on the left should be a little bit smaller than the one on the right. When we look at this series like this is not a series that we know converges or diverges when it's written in that way. But doesn't that then reduce down to be a 1 over n squared? 1 over n squared is a p-series. So we've reduced that through the comparison test down to a p-series. So if these two guys are the same, they're equivalent to each other, and my series is less than one of them, then it has to be less than the other. So isn't this series we're concerned about less than a p-series that also converges? So this guy would converge itself. So it converges without having to alternate. So this would converge absolutely. And then this is a handful here, because now we've got a couple things here. We're going to say that we did the comparison test for the non-alternating part. and it was less than a p-series with a p equal to 2. All right, so a lot there. Number 5, jump to this one. Alternates, so that's good. May want to clean this one up a little bit. We'll do a -1 to the n plus a 1, and then keep the n minus 1 squared in the numerator. But then in your denominator, we get 3n squared plus 3n. We alternate, so that's this element here, definitely alternating. So then the only thing that has to happen is this has to give us no negative terms and have a limit of 0. So does this in the parentheses here satisfy those things? Does it always spit out positives, and is it going to have a limit of 0? So as n goes to infinity, is this limit going to be a 0 or not? No, right? If those degrees are the same, so we have a degree square here, a squared right here, that means we look at their coefficients. So we have a coefficient of 1 here, coefficient of 1/3 right here. So this limit wouldn't be a 0. It would have been a 1/3, and it must be 0. So this right away then diverges. And that's our whole nth term test. That as we went to infinity, that limit would not have existed. All right, D and E. All right, number 6. This I do want you to do. I do want you to cross this out. So pretend that's not there. I don't want that there. Not everyone's going to be alternating right now, but I do want us to kind of see how this is going to play out. So now we're going to just determine, does it converge? Does it diverge? There's no absolutely. There is no conditionally. So when we look at this guy here, we have to do the nth term test first, and we should be good. This definitely has a limit of 0. The faster function is in your denominator, so we satisfy that part of the nth term test. Then we now have to start going through these. Is this a geometric series? Definitely not. We would then look, is this a p-series? It looks good in the denominator, but it has to be a constant in the numerator, and it's not, so it's not that. This will keep you busy for a while if you want to try to integrate that. So don't really want to have to do that or even try to do that. We can try the ratio test. Maybe we will, just as a little refresher. And then the comparison test. So most people, when they don't know what they're doing, will do the ratio test because they like the ratio test. It's very systematic. Do not write this down because it's not going to work. But the ratio test is that n plus 1 series divided by the original series. So here's the n plus 1 series. Instead of dividing by the original, I'm going to multiply by the reciprocal of the original instead of dividing by it. And then if you've watched that, remember the natural log one where we talked about the natural log of n plus 1 versus the natural log of n? Something similar is going to happen here. So if I give you the sine of n plus 1 over the sine of n times n squared over n plus 1 squared, for sure, this is old. Doesn't this have a limit of 1? They have the same degrees. As n goes to infinity, you look at their coefficients. What I have highlighted in blue is going to be a 1. Just like that natural log type on the video, basically the same exact thing is going to happen here. Think about if I did the sine of 1 billion and 1 and divided that by the sine of 1 billion. Doesn't this one really become completely inconsequential? And this is pretty much going to give you a 1 as well. The issue then, right, in the ratio test, if we get a 1, then that's always very disappointing because you just did quite a bit of work and it doesn't tell you anything. All right, so ratio test would be a good idea. It just doesn't work. So what you are then left with is the comparison test, the one that nobody has ever liked in all of my years of doing this because it's the hardest. But what we can compare this to, leave your n squared alone. And then what we're going to compare it to is 1 over n squared, because isn't 1 over n squared a series that we know converges? That's a p-series that converges. Remember your old amplitude days with the trig functions? What's the largest value that the sine curve could ever take on? 1, right? For the amplitude, that's the biggest value. So isn't this series always less than? And remember, we can also say equal to. So as long as it's less than or equal to, wouldn't this always give us values that are less than or equal to a convergent p-series? So this one does converge, and it's a comparison test. With our comparison test, it is less than. Do that first. A p-series with a p equal to 2, which is less than 1, or greater than 1, sorry. All right. All right, 7. See what you think for 7.